Hey everyone, so I'm Grant, and today I'll be presenting some of my work. Just looking at fluoride exposure to the benthic zone, like being said, and I'll use the word benthic zone quite often. And the benthic zone is just in streams in the stream bed, so it's basically the stream bed to about 50 centimeters below the stream bed. So it's kind of this top layer of dirt and stream. We get a lot of frogs and mussels living in freshwater environments. So first, some background. So chloride in streams is figure here that shows some streams in the GTA, the average chloride concentrations, and they've been increasing over the years, especially in the summer, which is all the red dots. In the winter, it makes sense for chloride concentrations to be high because typically around here they come from sodium chloride or road salt. So road salt de-icer in the winters, but it's kind of surprising to see these increasing concentrations during the summer months because there's more road salt used during this time. The thought here was that since these summer chloride concentrations are increasing, this may be due to groundwater inputs because summer chloride or summer stream concentrations are often controlled by discharging groundwater. So now another study here looked at these shallow groundwater chloride concentrations around streams. That's shown in the figure on the left, which shows these groundwater chloride concentrations are often higher than surface water concentrations in the summer months at least. So what does this mean? Well, high chloride concentrations in streams can be toxic to aquatic organisms such as mussels, zooplankton, and fish. And so because of this toxicity to these species, Canada set toxicity guidelines. So the long-term chloride toxicity guideline is 120 milligrams per liter, and the short-term is 640. So this is based on just toxicity tests in labs. So not every species is going to be impacted exactly over 120. It's just kind of a generalization for the most species living in freshwater environments. And then discharging groundwater, which is what I'm looking at, poses the greatest threat to this benthic zone that I explained earlier. Because when you get road salt coming in here at the road, then it can travel in the ground and come up in the stream bed where you get these bugs and mussels living, where they'd be most greatly impacted by these higher groundwater concentrations. So my objective is to evaluate the spatial and temporal exposure of chloride to the species living in the benthic zone. And to do this, I did field research at 2 sites, or 2 urban streams shown here, one smaller stream, the first one, and a bigger stream. So the small stream's about 2 meters wide and the bigger one's about 10 meters wide. And the small stream actually discharges into the bigger one. And they're both located in the southern part of London. So at both these streams, I measured chloride and sometimes electrical conductivity, or EC, which is a proxy for chloride. So high electrical conductivity means high chloride. So here's the first site, that's me over there on the right. And then I measured chloride along the length of this stream just to try to find a specific area of interest in it. And this red spot in the middle had the highest chloride in just the stream water itself, expected to be because of this road that the stream intersects, as well as this parking lot, which could be a source of road salt in the winters. So I chose this area as my study area for this site. And here I did pore water sampling. So pore water sampling is just using these wells that you see, little stream tips installed about 20 centimeters deep here to sample. And then it's about every 5 meters along the bank where I can collect water from 20 centimeters below the stream bed and measure it for chloride as well as some other things. But for this presentation, just focusing on chloride. I also did time-lapse geophysics. Geophysics just measures the electrical conductivity below the stream along these areas. So I can see high electrical conductivity or low EC associated with high or low chloride contamination. And then also stream bed EC. So this just measures the electrical conductivity at the top of the stream bed across the width, because all the groundwater samples are only along the bank. So it's just to get an idea across the entire width of the stream. So now getting into some results. So here, this figure, I'll explain it. The X-axis is location along the stream, so negative values are upstream of the road and positive values are downstream of the road or left and right of the road. And then chloride concentrations on the Y-axis. So, and then this red line is the acute toxicity guideline and the black is the chronic that I outlined earlier. So basically, the chloride concentrations measured in the pore water from the wells that I showed earlier are often higher than the toxicity guideline and nearly always higher, and often always also higher than the acute toxicity. Sorry. Meaning that species living in this benthic zone are experiencing chloride concentrations greater than what Canada has outlined to be reasonable for them. Also, there's a lot of spatial variability here. So you can see the concentrations increase and decrease by over 2,000 milligrams per liter over just 5 meter spans. So future research wants to assess if a roadside environment is contaminated by salt. It's important to take more than one sample because to get a representative idea, clearly it's quite variable. Now looking, since I said earlier, these ones are just along the bank. So looking across the entire width of the stream using the EC map, the yellow zones are the high EC or high chloride contamination. And where you get these high chloride zones in the pore water, typically they span across the entire width of the stream. So you get this kind of high exposure to aquatic species across the entire width. Now looking at depth, so this is using the geophysics where it's just measuring electrical conductivity below the stream to 4 meters depth here. And the red zones are high EC, which is associated with high chloride. So these high EC zones kind of align with the high chloride zones measured in the wells. And they extend to about 3 or 4 meters depth. So the wells are only 20 centimeters deep, so near the surface. But where these contaminated zones, it seems like the exposure actually goes to about 3 meters depth below the stream. So species, you can't just burrow a little deeper if you're at the top to try to avoid it. However, it does seem like maybe you could go kind of laterally or farther away from the road to get away, as the exposure in this stream is only high to about 40 meters upstream and downstream. Now looking at some temporal trends. So here, these are the chloride concentrations in the kind of the high zones where the chloride was higher than the acute toxicity guideline. And here, these concentrations are persistent year round, so they don't increase or decrease based on the salting season or winter or summer, as you'd expect with surface water. And then when comparing to the surface water, which is this gray line, you'd see it's highest in the winter or around February when road salt's applied. But the groundwater ones are high or consistent year round. The surface water one also in the summer, it decreases and then it's kind of controlled by flow. So during rain events, the concentrations decrease, whereas the groundwater ones are consistent regardless of flow. So species can't kind of evade the high chloride concentrations in the ground in the summer months. Now looking at the locations where they're still high, as in higher than the chronic toxicity guideline, but not crazy high like the acute toxicity guideline. And these ones are more variable, and they're actually higher in the salting season or around February, like the surface water. And it's expected in these areas, they're more controlled by surface water pushing down into the stream based on some other research. So when you get high or salty surface water in the winter, it's pushing down, impacting it. And then in the summer, there's a bit more relief. The final temporal thing here is for the geophysics. So this is once again, the depth below the stream. And then these are just a few snapshots throughout the year. But the main takeaway here is that these EC zones are persistent year round, as shown in the dedicated tip samplers. Also, the size of those is actually highest in the summer, like August and June. You can see this -10 one. So this just would mean that there's potentially a delay from when salt is applied in the winter to when it is discharging in the stream in the summer months. However, generally, they're still there year round. Now, looking at my second stream, this is the bigger of the two. Once again, we did this kind of longitudinal chloride thing in the stream to find a zone of interest. It took a long time and was, tiring, even though it doesn't look like that much. But so we found out this spot here. And once again, we did this pore water sampling. I got the other ones with these white screen tips and the stream.EC map. I didn't do geophysics here because the larger size of the stream makes it more difficult to work with these electrical techniques. So this kind of just supports the first stream just on a bigger scale, where the chloride concentrations, once again, is negative being upstream, positive being downstream of the road. The chloride concentrations are above chronic toxicity guidelines and sometimes even above acute toxicity guidelines in this area. So even though at the bigger stream, you're still seeing this similar exposure in the stream bed. At the stream though, actually the high chloride concentrations extend further to about 70 meters away from the road compared to the smaller stream. This could be just due to flow paths or travel times. It doesn't actually have to do with the stream here. It's just probably by chance. And then looking at the EC across it, once again, you can see where you get these high chloride zones. They're generally across the entire width of the stream. However, once you get past 40, it kind of skews just to the one side. But for the most part, chloride is discharging across the entire width of the stream. Now looking at the temporal trends at this larger stream, once again, the chloride concentrations in the ground are higher than the surface water, the light gray being the surface water, high once again in the winter, and the groundwater ones are generally high throughout the year, with some fluctuations, but still generally higher than the groundwater, meaning species living in this benthic zone or this top layer of stream bed are experiencing higher chloride concentrations in the non-salting seasons, especially in comparison to the surface water. Now, looking at locations that are lower chloride, they're once again more variable, typically higher than the chronic toxicity guidelines still throughout the entire year. However, actually, once you get towards November, they do dip below it. So finally, just some key takeaways or conclusions. So that the chloride concentrations in these stream bed where you get fish eggs and mussels and zooplankton living are often higher than the toxicity guidelines outlined by Canada, meaning that it's toxic to species living here, and that the concentrations can extend to about 30 or 60 meters away from the roads. So if conservation authorities or other groups are interested in doing stream reclamation projects in the future, it's important to understand these roadside stream bed environments are not safe for new fish species or juvenile mussels. Also, the chloride exposure can be very highly spatially variable. However, it seems to be persistent year-round in all the zones where chloride is quite high. So just finally, thanks to the students in the group that all helped me with this research and the funding agencies. Thank you.
Questions for a speaker? I have two. The first is are these very high chlorides consistent, for example, just when they're discharging, after a snowfall or something, or is it relatively stable?
The chloride in the
Yes, really high peaks in chloride content.
Yeah, they're so like this one here is -10, so it's this line here. So there are fluctuations, but it's pretty stable throughout the within the summer, it's still around 5,000 milligrams per liter. So it's not just during the salt or the winter season. It indicates there's probably just legacy chloride or so much salt has been applied that rather than we thought there'd be a salt plume, then a fresh plume, and a salt plume, but it seems to be just salty year round. So I think there's just so much salt kind of in the micropores, and so it just keeps coming out throughout the entire year.
Also, there's enough of a reservoir basically.
Yeah,
we'll just keep.
Yeah, it doesn't actually ever seem to wash away yet. Maybe if we stopped using salt, eventually it would, but now it's just kind of consistent year round.
Scary. So if I were cycling, should I be worried about rust even in summer?
No, because this is just in ground water.
Okay,
it's just right below the stream. Yeah. Something.
You show only summer photos.
Yeah, this one.
Oh, I see.
Yeah.
Are these waders or how?
Yeah, just hit waves. Yeah, that day was actually too cold, so I just took a picture and left.
You know the secrets behind the data. Excellent. Other questions? Yeah.
Do you have any idea why there's sort of an asymmetry on the different sides of the road? Like the peak seems to be on one side and then on the other plot it's on the right side. Do you have any idea why?
For this one, it kind of goes down here, and that's because it becomes a lot finer material, so it's harder for the water to flow, we suspect at least. So, and then this big peak here, the biggest one is associated with this parking lot. So the parking lot piles snow there, so the highest peak is coming from the piled snow from the parking lot rather than just off the road. For the other side though, the bigger stream, I'm not exactly sure. We think that just probably flow paths on the side where it's lower, there's more paved area on the side of the road, so maybe there's less what's all infiltrating into the ground there. Or better stormwater. There's a stormwater reservoir like pipe there, so maybe more is just getting washed off as runoff and less infiltration, but we're not exactly sure.
Thank you. Thanks. Okay, so. By the way, I forgot to mention that there actually is money on the line, as we do every year. There's, I think, $200 or $300 of prize money for the top 3 presenters per round. And thanks again to Professor Jin Wang for agreeing to judge the student competition. Okay, so our next speaker is Shaoqing, supervised by Professor Ashraf Al-Damati, who will be presenting to us on the parametric study of the response of wind turbines under F2 tornadoes, considering the effect of angle of twist. Please. Yes, the lead works, but the thing is a bit laggy. So.
Okay, hello everyone. My name is Shaoqing Yu. I'm under supervision of Professor Ashraf Al-Damati, and the topic I'll be presenting today is parametric study of response of wind turbines under tornado loading, considering the effect of angle of twist. So this is today's table of contents. So first, let's start with some introduction. Wind energy has been growing rapidly throughout the years, and usually wind turbines are used to harvest that energy, and there are usually 2 types of wind turbines, onshore and offshore. And my research, we only focus on onshore wind turbines. And those wind turbines are usually located in rural regions. That means it's easily exposed to high intensity wind events. And one of that event could be tornadoes. So tornado is quite different. It has some interesting characteristics. So first, it's a sudden and a localized event, and it could happen any location with respect to the wind turbine. And also, if you look at the wind profile, it's very different from the boundary layer wind. And I believe this picture is actually taken a year ago in one of the wind farms in Texas. And it was hit by like an F2 tornado, and many of the wind turbines are damaged, and most of the damage has actually happened to the blade. The interesting part is if you look at closely, you see there's one wind turbine which survived because the sudden and localized nature of this tornado. So that brings us to the research gap. There's many research has done related to this topic. And usually they only consider one type of wind turbines. And then the second gap would be they did not really consider the random nature of tornadoes. And we have did some similar works in our research group. However, they did not really consider the effect of angle of twist. So that brings me to the objective of my study. I want to develop or modify an existing numerical code that can capture this response of wind turbines after under tornado loadings, and also considering the effect of angle of twist. And eventually, I want to use this numerical code as well to do a parametric study so that we can analyze the critical tornado locations and also the optimum blade pitch angles. So I believe this is a very nice flow chart that shows you the logic of the numerical code that we developed. So first we have to define the structures, and then we have the tornado loading, which is the CFD data that was done by Dr. Hodgins' team years ago. And then for the parametric study, we have 2 different loops. The outer loops is that we're changing the location of the tornado. So we use 2 parameters to define the location of the tornado. One is R, which is the distance from the center of the turbines to the center of the tornado. And then theta is just the attacking angle of the tornado. So that way we can change the locations. And the inner loop, we're actually changing the blade pitch angles. So that way we kind of considered all the possible cases of the tornado and also our wind turbine blades. So we can obtain the critical configurations of the tornado and also the optimum blade pitch angles. So now let's jump into some details. So they are the equations that we use to calculate the forces. So for the tower, it's actually simple because there's only drag forces, which is CD. That drag little coefficient here. And then for the blade, it's more interesting because not only we have drag forces, but also we have lift forces. That means not only we have to compute the drag coefficient, but also lift coefficient. The drag coefficient for the tower is always a constant value throughout the tower for the entire section. However, the blade looks more like this. So the CD and CL values could be tricky. I guess we just doesn't wait the picture.
At the bottom.
So how can I get this drag and lift coefficient? So if you look at this figure 8, so the solid lines are the one that represent the lift coefficient, and the dotted lines are the one represent the drag coefficient. And the horizontal axis is called angle of attack. So basically, if you know the angle of attack, you can read the drag and lift coefficient from this figure. And then the question becomes, how do you get the angle of attack? So angle of attack is defined by two angles. One is the phi, the bigger angle, which is the attacking wind angle. And then beta is actually the pitch angle, because we're changing pitch angle from 0 to 90. And then if we know the wind component, we can easily calculate this alpha. But if you remember my topic, I'm also focusing on angle of twist. So where should I apply this angle of twist? So the angle of twist can be considered as part of the blade pitch angles. So usually when they design the blade is not a flat piece. So it comes with a naturally twisted, this little angle here. So it starts from the root, usually 10 to 14 degrees, and it decreases until you reach the tip of the blade. So basically the final equation can look like alpha equal to phi subtract beta subtract this angle of twist. Then for the CFD, we're using Dr. Horan Hagen's James value. So tornado has three components, tangential, radial, and vertical. And usually tangential component can cover the design because it's larger. And then I also plotted them in different graphs. I'm changing the distance, moving away from the center of the tornado. I think the R starts from 96 and all the way to 288. So you can see if you are moving away from the center of the tornado, the profile looks more like a boundary layer wind eventually. We did a nice validation with FAST, and however, FAST does not really consider tornado loading. So basically, we are replacing our wind field with a synoptic wind in our code. And then we can analyze the same structure under same loading. And we got pretty good agreement between those two. So for the case study, I consider three different wind turbines, 1.5, 5, and 10 megawatts. Usually 10 megawatts a little big for onshore wind turbines, but I'm just putting this here and so that we can have a nice conclusion with variable sizes wind turbines. And the mean difference are the sizes. You can see all the parameters are given here. The diameters is changing from 70 to 178, and then also the hop height and everything. So now let's look at the result. Usually when you look at the result for wind turbines, you focus on two locations. One is the root of the blade. The other one is the root of the tower. So for the blade, our software can compute two different bending moments. One is flapwise, the other one is edgewise. So if the blade is like this, flapwise direction would be this, edgewise would be this. So if you look at the result, usually the edgewise bending moment is smaller. And however, for the blade, it's actually stiffer this direction, which makes flapwise bending moment to be more critical. So basically, I only plot the flapwise bending moment here. As you can see, I have dotted lines that represent the value considering the effect of angle of twist. And the solid lines are the ones that does not consider angle of twist. And then three different blade, 1, 2, 3, and blade 1 is pointing upward, 2 and 3 are going like this. And this is for the 1.5 megawatts. I'm changing the blade pitch angle from 0 to 90 degree so that I consider all possible cases. So you can see that the angle of twist has a positive impact to the result, which means if you don't really consider this in the design, you could be underestimating the load. And it is very easy to say that 90 degree gave you the least bending moment, at least for this one wind turbine. And for the actually for the angle of twist, it makes sense because the reason why they have angle of twist design for the blade is that they want to maximize the lift forces. So they want to make the thing rotating quicker. Okay, so that's why you can end up with a larger force. And I have this plotted for the 5 megawatts, similar conclusion is positive impact for the angle of twist, either 0 or 90 degrees. But here we're looking at the dotted lines, so I can say 0 degree give you, 90 degree give you least bending moment. And the 10 megawatts follow the same trend almost. And now we can move on to the power-based bending moment. So there are 3 different bending moments considered here: in plane, out of plane, and the resultant. So the green line are the resultant bending moment, and still same trend here. Dotted lines represents the angle of twist. The other one does not really consider. And we can see positive impact and we give you the least amount of bending moment. Similar trend here, either 0 or 90, but I would say 90 just to make it the same for all 3 wind turbines. So now I can have my conclusion. First, I can say that blade pitch angle equal to 90 is the most optimum blade pitch angle. And then I have 2 different bullet points here. It says the critical locations of the tornado for the blade or the tower. That means when the critical case is happening to the blade, that may not be the same cases for the tower. So that you have to consider 2 different scenarios here. And I can conclude that considering the angle of twist, it has a positive impact to the wind turbines. And some future work directions, I want to compare this with the current design load cases to see which one really governs the design. And then because the CFD data we have is from run simulation, so we didn't really consider turbulence. And in the future, we definitely want to consider tornado turbulence, which means we have to do dynamic analysis. And that's the case, I have to consider flow structure interaction, etc. And eventually, if we have time, especially money, we can do some nice experimental work at Windy, and then that'll be a very good comparison between numerical work and experimental work. So I think this is all I have. Thank you.
Questions to the speaker? Yes.
Okay, so what are the drag coefficient and lift coefficient for the tornado?
Yes. So usually, if you look at this blade, they divided the blade. When they manufacture the blade, they divided the blade into little elements. And for each element, it comes with one of this. Some of them could share the same graph, but they have usually 4 to 5, or for 10 megawatts, I believe I have 30 of them. Look similar but different. So the drag coefficient in that equation is here. So we have half times air density times velocity squared times the coefficient and the CD value. I think, oh, this is the chord length, that's for the member itself. So basically, this is just a coefficient. It's changing from, I believe, almost -1 to positive 1.5. And then if you want to get the forces, you have to get this coefficient that has no unit. And then this is related to each element of the wind turbine's blade component.
So these coefficients are actually from boundary layer winds, not from.
I'm not sure because when they design the blade, they come with the blade. So we're not like calculating those coefficients. So yeah. That's good. Thanks.
So our third speaker in the afternoon is Sabrina Jivani, who is supervised by Professor Claire Robinson, as was Grant, forgot to mention. And she will be talking to us about modeling water quality in a cold climate, urban water sub-watershed. Thank you.
Yes, so I'm Sabrina, and I'll be introducing the topic that I've been working on, which is modeling water quality in a cold climate urban sub-watershed. So just to start off with a little bit of background, excess phosphorus loading has been contributing to harmful algal blooms within the Lake Erie Basin and also just freshwater lakes overall. We've understood, and this can be really harmful to ecosystems, the ecology, and the recreational industry as well. And we've kind of understood a lot about how agricultural phosphorus inputs may be contributing to this. However, we don't understand too much about urbanized areas, and we haven't really quantified much phosphorus loads from urban areas as well. And as urbanization continues to increase in Southern Ontario and Ontario in general, it's important to understand this. So they need to be better quantified and better understood to be able to inform land management and stormwater management strategies for the purpose of improving water quality.
I have a specific study site for which we have collected field data. A previous student has done the field data collection at work for this. And it's Thornycroft Drain in London, Ontario. It's approximately 6 kilometers squared. And this map kind of shows the variety of land uses it has. So it's a mixed urban land use sub-watershed. So it also has a little bit of agricultural areas. And the black dots there represent the sampling points that we had. So we had sampling points at the inlet and outlets of LIDs. And I mentioned up there's also a wet pond, so we also looked at that. And then we also have sampling points at the sub-watershed outlet. And there's 2 rain gauges that are unfortunately outside of the sub-watershed, but at least there's one on each end. So my objective specifically is to be able to provide information that we may be missing from field data, specifically seasonal and annual phosphorus load estimates. I want to analyze the LID effectiveness after I create this model using modeling scenarios, and also predict changes with urbanization and climate change, again, using modeling scenarios. So I have to be able to complete this objective, I have to be able to model water quantity and quality within the sub-watershed. And this addresses a few research gaps, one of which being there's not too many cold climate models. One of the reasons being it's kind of hard to get field data from the winter season, and we've been able to collect some field data for that. There's also not too many studies conducting LID modeling at a watershed scale, and then also looking at the effect of urbanization, specifically when you're looking at water quality and phosphorus loads. And then also there haven't been too many studies that do model calibration with extensive field data. A lot of studies use a few events or design storms. So we have a lot of field data to be able to reduce uncertainty in this model. So my methodology can be summarized here in this chart. I started off with the event-based hydrological model, and I used PC-SWIM. So PC-SWIM incorporates SWIM, which is the stormwater management model created by US EPA. So I created the hydrological and hydraulic model. I did a sensitivity analysis using a manual one at a time method. Flow calibration. The flow calibration was done using a tool in PC-SWIM called the SRTC tool. And essentially what this helped me do is optimize the NSE value. So this is a value that's comparable to the R-squared value, where a 1 indicates a perfect match with the field and the model data. And my objective was to have an NSE value greater than 0.7 and the volume and peak flow within 30% of the observed data. And then I also conducted flow validation. And you can see the number of events I used for each part. I also did a continuous model just because I wanted to be able to calculate the yearly and annual, the seasonal load estimates. So this was done using the event-based model, and then I also had to incorporate different parts of what you need in a continuous model, such as evaporation, soil recovery, the recovery rate. And I had a similar objective, NSE value of 0.7, and the volume and peak flow within 30%. So when I created the hydrological and hydraulic model, I had to use a lot of different types of data. This included doing a GIS analysis, design drawings, literature values. I used field observations as well, and then open government data, for example, for the storm sewerage. And I have my SWIM model with 53 subcatchments. I also conducted a multi-site calibration instead of just calibration using the watershed outlet. Because we had the field data for that. So you can see there's multiple different sites that represent the outlets of different land use areas. And then also some that represent the outlet of LIDs, for example, we have Israel. And the precipitation events that I used for the event-based model vary. And this is just kind of to show a general graph of the different types of events I used that ranged in rainfall depth. And I tried to capture the larger events as those are more estimated to be contributing larger loads in general. And then also for the seasonal pattern that I incorporated, I had to use a lot of events for the different months. And so far I haven't incorporated snowfall and snow melt, and that's a major aspect of the cold climate model, and that's something I have to do as well. So I mentioned the seasonal pattern. These are the parameters I use the seasonal patterns on. So that's depression storage, which is the amount of water, the impervious and impervious areas. In impervious areas, this might change because you have tree canopy covers which can intercept rainfall. So that's kind of represented through depression storage here. The pervious roughness of the area increases in the summer months, and then also the infiltration increases. And these were all calibrated using the SRTC tool as well. And then I just went back and checked if it made sense with what you'd expect with increasing vegetation and also the growing season for the agricultural land uses. Here are my results. These data points represent all the different locations and events that I have. And as you can see, majority of them did fall above an NSC value 0.7. And there were a few that did not. And those were areas that we had trouble calibrating. One of them was an area where we expected there to be backflow in the storm sewer, and that was kind of difficult to calibrate. And for the continuous model, without going too much into it, I added in temperature data to be able to, what SWIM does is create use a sinusoidal curve to be able to create varying daily temperature data. And then also I had to add in a soil recovery pattern as this improved the model. And this changes the infiltration capacity of the recovery rate for throughout the month. So it kind of just changed in the summer and fall because in the fall it's more wet and the summer is a drier season. For the water quality model, I went with the buildup and wash off model. So it's kind of summarized here. You can see in the graph, I used the exponential buildup and exponential wash off model. And you can see in the graph what the exponential model would look like. And this is over a rain event. And I had 4 coefficients to calibrate. It was a C1 to C4 that's listed up there. And I had to calibrate these coefficients for each of the pollutants that I was modeling. So I mentioned phosphorus, but we also had TSS data, and that's correlated with phosphorus. So I modeled that first, and then I modeled total phosphorus, and then there is soluble reactive phosphorus, which is the bioavailable form of phosphorus. And this was unique to each land use. So this allows us to be able to change land uses and see how the water quality would change when I'm conducting modeling scenarios. And my methodology was pretty similar to that for the hydrological model. I started with values that were informed from literature. However, this is kind of considered like a black box model, so it really changes for depending on the site. So I used the SRTC tool again to calibrate these coefficients. And you can see the number of events that we had from our field data to calibrate it. And then it is harder to calibrate water quality events. So I used an NSC value 0.5 as my criteria. And I wanted the event mean concentration and the total load to fall within 30%. And what I found through this was that I had to use a seasonal average, which kind of indicated that the way the buildup and wash off model at least works in the subcatchment is different in summer and fall. And then I did the continuous model as well for TSS. And then I did a continuous total phosphorus model. So here I wrote that I prioritized high load events because I found it pretty hard to model total phosphorus and because there are pretty low load events and high load events. We wanted to be able to capture the greater amount of phosphorus that was coming out of the subwatershed. And finally, I have to conduct the calibration and validation for the SRP model. Just to show kind of what the result would look like or what a good result will look like. This is a zoomed in part of the continuous model. It's just one event. And you can see when the model results are good, the concentration and loads line up pretty good compared to the observed model, which is, the observed data, which is the red line, and then the yellow data, the yellow line, which is the model data. And I was able to obtain load estimates as well. And then the next steps include modeling SRP, as I mentioned, and then conducting the scenario analysis. And that's a picture of the watershed outlet for a subcatchment. Thank you for listening, and please let me know if you have any questions.
Questions from our audience? No questions. I have just one.
Yes.
With the discontinuous models, are you selecting then the concentration at a given time after the rain event? What is that time?
We have field data that we collected, and it's kind of like high frequency data. So it's collect we have multiple data points within the event itself. So I'm using all the data points and
Using multiple.
multiple data points for each event. Yeah.
This question.
So can you go to the the result of your like concentration and flow. Yeah, so for your concentrations, you see the like the post event, like the constant value, why it's so different? Because for your flow and your load is kind of made like the result net, but the concentration is kind of have a gap. You don't know what caused that.
For which part of the
Concentration, the post event value.
post event?
Yeah.
It just goes a little bit lower. So the load is calculated by multiplying the flow and concentration. So the flow, because the flow is a little bit lower, the load will always be a little bit less. Does that make sense? But the last data point, the field data point and the concentration is represented by that last dot. And then after that, it's just pretty low because the event has ended. Yeah. Yeah.
For the precipitation events, how do you define a high precipitation event?
It's just the amount of, I can go through the graph.
Did you set a specific threshold or something?
So I'm just looking at the rainfall depth. And I look at, so we have precipitation data, 15-minute precipitation data from 2021 to 2023. So this is, yeah, so that's one of the largest rain events that we had. And then there was a larger one in July 2023 that I don't have here, but that I also used. So these are just the larger events that occurred in this time period in general. Yeah.
Thank you. Okay, last but not least. All right. Our last speaker, Nima Farasat, supervised by Professor Tim Newson. He'll be speaking to us about modeling in soft aqueous granular soil.
As you can see, the research topic is tunneling soft saturated granular soil. And the content for this presentation is introduction or the background, volume loss parameters affecting volume loss, analytical prediction, research gap, tools, model, and results. The growth of human population in corridor cities like Toronto, Vancouver, Ottawa, or some other cities like that, increase our needs for underground tunnels, which solves the traffic jams and infrastructure issues. The designer's preference is shallower tunnel, but although it is cheaper, it increases the risk of damaging structures on the surface. So we have to do something about that. Soil excavation increase the surface and actually cause surface and subsurface movements. When we want to talk about surface and subsurface movements, we have to take volume loss into our consideration because it plays a main role in this area. What is volume loss? Volume loss is a volume difference between the head of tunnel and the tunnel that is built along the tunnel. I mean the ring. That volume difference is called volume loss. As you can see, the gray area over there is called volume loss. It has several factors depending on the type of soil. For example, for sand, we have a volume loss at the face of the tunnel. We have a volume loss above the conical shape of the TBM. And we have a volume loss at the closure of the tail void. For the clay, if you want to work on clay, we have to think about volume loss due to the consolidation along the tunnel. As I said, there is a difference between the type of soil. For the sand, volume loss is about 0.2% to 3%, typically around 0.5%. For clay, it's about 1 to 2%. For unexpected occurrence like sinkhole failure or something like that, it may increase to more than 3%. most of the time 6 or 5%, which cause a kind of disaster. Think about a city like Toronto. In the downtown, you wanna build a tunnel or something like that. If increase that much, it may cause falling the buildings and hitting each other, the other buildings or something like that. It may cause killing some people or maybe cause some disasters. The actual value depends on several factors. The type of machine, the TBM machine that we want to use, earth pressure machine or silvery machine. It depends on the operator and period of active support pressure to holding soil moving toward the excavated hole and some other stuff like that. If the applied pressure provided by TBM is less than both soil and pore water pressure, we have some settlement. And if it is larger than those ones, we have heat phenomena. In both cases, we may have some problems. So in that case, we have to make sure we provide enough support pressure. For undrained soil, volume loss at the ground surface and tunnel level is the same. Undrained soil like clay. For drained soils like sand, actually volume loss at the ground surface and tunnel level can be different. So in that case, if a designer try to set a targeted volume loss at the tunnel level, it is not the same as ground level, so it may cause some problems. It may result in settlement or heap or something like that. The volumetric behavior of the soil is very important. Most of the time we have it in sand. If we see the dilated soil behavior, volume loss at the ground surface is less than volume loss at the tunnel level. But if we have a contracted soil behavior, it shows the inverse actually behavior. For sand, as you can see in this picture, the volume loss is somehow localized above the tunnel crown, but for the clay, actually it is somehow elliptical around the tunnel. So the type of soil somehow determines the shape of actually volume loss that we have to face. So analytical prediction. We have several methods for predicting settlement on the surface and tunnel level. Because of the limited time, I just mentioned two of them, the empirical ones. For surface, as you can see here, we can calculate volumes at the ground surface using this formula. I is a very important factor, which is called inflection point. As you can see here, it is the distance between the middle of the tunnel to the inflection point, which is the change of slope in the curve that we have on the ground surface. And K is important as well for the surface based on orally and new actually study. K constant for clay can vary between 0.4 to 0.7, and for sand it can vary 0.2 to 0.3. For subsurface, as you can see, we have to calculate K value, and I is different as well. They are not the same, so we have to take it into our calculation and consideration if we want to calculate subsurface settlement. Okay, research gap. So there are lots of research have been done on clay soil, and if there is a few research have been done on dry sand, but there is a lack of knowledge about saturated one. So based on the literature, dry sand tests are not applicable for saturated one. Even we account for actually water pressure and take it into consideration for our actually our design. So we have to do some research about this one. Actually, so so in that case, I like to do that. For doing that, I have to use several tools. Two main of them are centrifuge. I think one of them is centrifuge. As you can see here, it's a 4 meter tall, 2.2 meter diameter. It can reach to 450 G Earth's gravity. It has the one tool table, which is in the middle of the centrifuge. This one is the drum. This one is tool table. They can rotate separately, or they can rotate synchronously. And using this table, we can convert the model results to prototype results, or inverse, using this one. And another tool that I'm using is camera. So as you can see, the left picture is like a curvy shape picture, which is not a good one for image processing. So I faced a fisheye problem. This one is the fisheye problem. So using Traco, and I try to calibrate my camera to correct the picture to this one. Then I use the particle image velocity to track the pixels in each picture. Actually, the thing that I'm doing, I record a video and convert it to a series of pictures. Then I put a mesh on the first one and put a 1 point as a nominal point for each patch. And I track that point in several, in the series of pictures. Using that one and using LSF, linear standard factor, I can convert the binary dimension to actually a physical dimension. So using this one, I can obtain the displacement or something that I want. This model is one of my preliminary arterial one. So I use the air pluviation to have the uniform soil here. I put it inside the centrifuge, and this one is my camera. And as you can see, actually after running under elevated G 20, 40, 60, 80, and 100 on the top of the tunnel on the ground surface, you can see under elevated G, we have the different settlements. And you can see at the 100 G, so it squeeze the pool noodle. And we have this displacement. Honestly, here sinkholes happens. Okay, here I try to compare the results, the settlements that I have on the ground surface and at the ground level. As you can see, we have a different curve, we have a different trend, and we have a different settlement somehow. And as you can see, considering this calculation, we have a different volume loss at the ground surface and at the tunnel level, which proves the literature claims about this one. Thank you so much for your listening and control.
We have time for one quick question. If not, then thank you very much. And thank you all. Thank you to all the speakers.